In this video, we are going to talk about the solution of exact first-order ordinary differential equation. So let's assume that we have differential equation of this form, m of x and y dx plus n of x and y dy equal to 0. So this is a standard form of first-order first-degree differential equation. So we say that this first-order differential equation is exact if the following condition is satisfied. If we have partial m by partial y equal to partial n by partial x. In this case, if this condition is satisfied, then we say that this differential equation that we have is exact differential equation. And this condition here is sufficient and necessary. So it means that the differential equation, to be exact, it has to satisfy this property. And also it means that if we have this property, this is sufficient to say that the differential equation is exact. So this is necessary and sufficient condition. And if we have this property, we will have a very important conclusion, which is the solution of the differential equation is guaranteed and takes this form: u of x and y equal to c. And so we are pretty sure that we can find solution for the differential equation in this form. This is the importance of this property. So what is the meaning of this exactness property? It means that the differential equation that we have here represents an exact differentiation of some function u of x and y, and that's why we say that the solution is guaranteed. So let's take an example. Assume that we have differential equation of this form. We have 2xy plus 3x squared dx plus x squared dy, this equals to 0. So the first thing here, we need to identify which is our function m of x and y and which is our function n of x and y. And to do this, we don't just look to the order of these terms. It's not by order, it's the terms which multiplied by dx. This one here will be our function m of x and y, and this term here, which is multiplied by dy, will be our function n of x and y. So the first thing that we need to do here is to check for exactness. So we apply this simple test here, and we see, so partial m by partial y, and this equals to, when we look at this term here, we have 2xy. So here we will differentiate with respect to y, assuming x is constant. When we do this, we will have the differentiation of m with respect to y equal to 2x, and this term here, 3x squared, will equal to 0 when we differentiate with respect to x. So this is the differentiation of partial m by partial y. And here we do the same here for n. So we look for partial n by partial x. So we differentiate with respect to x, assuming y is constant. And here we have only the term x squared. When we differentiate it with respect to x, we will have 2x. So if we look here, we will see that partial n by partial x equal to 2x, and we have partial m by partial y equal to 2x, and so we have these two terms equal to each other, and so the property of exactness here is satisfied, and so this differential equation that we have at hand is exact differential equation. And since we have this property, so now we are pretty sure that we have a solution in this form that satisfied this differential equation. And since this solution here satisfies differential equation, if we differentiate it, we will have du, which we will have partial u by partial x dx plus partial u by partial y dy equal to 0. And since we assume that u is the solution of the differential equation, then the differential equations that we obtain from this solution must be exactly the same as the given differential equation. And from this, we conclude that our term here, partial u by partial x, which is a term multiplied by dx, will equal to our function here, m of x and y. And also our term here, partial u by partial y, which is a term multiplied by dy, must equal to the term n of x and y, which is multiplied by dy here in the differential equation. And from this, when we apply this into our example, so from this we conclude that partial u by partial x will equal to the function m here, which is 2xy plus 3x squared. And also we will have partial u by partial y will equal to the function n here, which is x squared. And from here we will use these two terms to find the function u of x and y, which is the solution of this differential equation. Okay, so from the previous step we have reached to this conclusion that we have partial u by partial x equal to 2xy plus 3x squared, and we have partial u by partial y equal to x squared. We will use these identities to find the function u of x and y. The first thing that we will do here, so we can start from this side here. So here we have partial u by partial x equal to this function. So this means if we integrate with respect to x and keeping y constant, we will have u of x and y will equal to the integration of these two terms, 2xy plus 3x squared, when we integrate with respect to x, plus we will have constant due to this integration. And since here we integrate with respect to x, so our constant here, it can be function of y. So in general we will write it like this, f of y. Of course it can be some constant which is not function of y, but this will be also included in this case of f of y. So from here we do this integration with respect to x, we will have u of x and y equal to, when we integrate this term here, 2x y, so we will integrate only x, so it becomes x squared over 2, and here we have 2, so we will have x squared y plus, when we integrate 3x squared, we will have the integration of x squared, x cubic over 3 multiplied by 3, so we will have only x cubic here, plus our constant function here, f of y. So it remains now to determine this one, how to find this function f of y. The simple trick here to do is to differentiate this function u of x and y with respect to y. So when we do this, we will have partial u by partial y, so we will keep x constant and we only differentiate with respect to y. For this term here will give x squared, and this term here will be equal to 0 because this is only function of x, and we have f of y here that we don't know yet. So here we will, the differentiation of this function will be something that we will denote as f dash f of y. And then we take this one here, so here this is our partial u by partial y, and we know from our previous conclusion that partial u by partial y equal to x squared, and so we make these two equations equal to each other, and from this we conclude that x squared plus f dash of y equal to x squared. From this we conclude that f dash of y is equal to 0, and from this we will have f of y is equal to constant, and if we can call this constant anything, so let's call it a for instance. And so now we have determined f of y that we are looking for. We take this one here and we substitute in our u of x and y to get the solution from this. So we say our u of x and y will have x squared y plus x cubic plus f of y, which is constant that we have called a, and this is our u function. This an important remark here, this is not the general solution of the differential equation, because if you remember we have said that the solution, our solution of the differential equation is this one, u of x and y equal to constant. So it's not just our u, but we have to equate this function u with the arbitrary constant c. So here the general solution will be finally as x squared y plus x cubic plus a equal to c, and here we have constant here and we have constant here, So it's not necessary to have two arbitrary constants. If we bring this one here into the left hand side, into the right hand side, we will have x square y plus x cubic equal to c minus a, and we can call this as just one constant. For example, let's call it p, and we know now that p is equal to c minus a. Okay, and so this now is the general solution of the differential equation. The last step that we need to do now, the last step that we need to do here is to check our solution, and this is very simple. So to check our solution, we have to make sure that partial u by partial x equal to this one here, and partial u by partial y equal to this one here. If this is satisfied, then the general solutions that we have satisfy the given differential equation. So here, if we look at this one here, if we differentiate with respect to x, this term will give 2x multiplied by y. So here we will have 2xy plus the differentiation of this one will give 3x squared, and the right hand side will be equal to 0, and this is typically this one here, partial u by partial x. And if we differentiate it with respect to y, we will have here from the first term we will have just x squared, because the second term will equal to 0 when we differentiate it with respect to y, and the right hand side will equal to 0, and so partial u by partial y is really equal to this one here, which is x squared. And so now we are pretty sure that this is this represents general solution to the given differential equation. Okay, so let's summarize what we have done so far. We have a differential equation m of x and y dx plus n of x and y dy equal to 0. So this is our given differential equation, first order, first degree differential equation, and we need to find the solution for this one. The first step is to check for exactness, and the simple test for this is to look for partial m by partial y, and we see if it is equal to partial n by partial x. If this is satisfied, then the differential equation is exact differential equation, and from this we conclude that the solution of this differential equation is guaranteed to be exact. Okay, secondly, since after we have checked that the differential equation is exact, we look for the solution of the differential equation in this form, u of x and y equal to c, and we by differentiating this one here, we equate partial u. From this we have partial u by partial x equal to m of x and y, and we have partial u by partial y will equal to n of x and y, and from these two formulas we find the function u of x and y. And don't forget at the end to say that our solution that we are looking for is u of x and y equal to constant. The last step that we do finally is to check our solution. So after we find the solution of the differential equation, we differentiate this one here, so du will equal to partial u by partial x dx plus partial u by partial y dy, and if our solution is correct, it has to be true that partial u by partial x is equal to m of x and y of the given differential equation, and partial u by partial y, it has to be equal to n of x and y of the given differential equation. So these are the three steps to find the solution of the first order, first degree differential equation if this given differential equation is exact. In fact, there is a shortcut to find the solution if we find that the given differential equation is exact, and this shortcut comes from the definition of exactness, because as we have explained before, the meaning that the differential equation is exact, it means that this differential equation represents an exact differentiation of some function u of x and y. And so if we look at this given differential equation after we have found that this differential equation is exact, we can make what we call grouping of terms to find this function that when we differentiate it give us or allow us to find this given differential equation, and from this we can find the solution directly. So let's revisit the previous example and see how to find this solution in a shortcut way. So in the previous example we have, so this is example one, again we have 2xy plus 3x squared dx plus x squared dy equal to 0. The first step, as we have done before, is to check if this differential equation is exact or not, and we will not have something different here. If we do the test again, we will find of course that this differential equation is exact. Once we have found this conclusion, we can look for these terms to find the function which by differentiation give this differential equation exactly. And if we look to this one, I can write this one here as this one d. So these two terms here represent the differentiation of this function here. So here, this one here will become x squared y plus x cubic equal to 0. So actually these two terms here represent the differentiation of this function. We can check this so easily. If we differentiate this with x, we will have 2xy plus 3x squared, which is this term here, which is a function m of x and y. And if we differentiate this one here with respect to y, we will have x squared, just x squared, because this one will equal 0, and this gives us the function n of x and y. So from here, if we integrate, if we make direct integration for both sides, we will have, so the integration here will counteracting this differentiation, and so we will have directly x squared y plus x squared equal to constant, and this is exactly the general solution that we have obtained before. So the key point here, if we find that the given differential equation is exact, we can make some inspection to the terms of m of x and y and n of x and y to find the function which by differentiation give the same exact differential equation. And this can be easy because this is first order differential equation, so the inspection won't be really hard to find this function u of x y in a direct manner. But otherwise, if you can't figure it out, that's okay. You can follow the systematic approach that we have done before and you will reach the same answer exactly. So I hope this was clear, and thank you for watching.